We want to select one lucky process out of all of those processes, and we want to send that lucky process to the CPU. Hello everyone, so I'm going to tell you in this video what CPU scheduling is, how we select processes to send to CPU, and by us we mean the operating system. So we'll be discussing how an operating system selects a process from a number of processes to send to CPU. So in most of the discussion of this video, we're going to assume that we have only one CPU, and if we have only one CPU, we are going to have to select only one process to send to that CPU. If we have multiple CPUs, we will have multiple queues of processes waiting to go in each respective CPU, and the operating system will select one process per CPU to send to CPU for execution. So this is called CPU scheduling. And CPU scheduling has so many different aspects to it, but before we go into those, we need to understand how good CPU scheduling algorithm can help us, or the operating system, to make good choices or to make best use of CPU time. So the operating system needs to find a way to make best use of CPU time. And in order to understand that, first we need to understand what different phases a process can go through. For example, it can opt to go into the CPU. For example, you have written a statement x equal to y plus z. So your program, in other words, is trying to go into the CPU and execute x equal to y plus z. Similarly, if you have written in your program printf or scanf or cin or cout or similar commands, that means that your program is asking for input-output operations like printing to the screen or getting a character from the keyboard. So these are called IO operations, or we call it an IO cycle for a process. So a process can go through different cycles, like it can go into the CPU, that is, we formally call it a CPU burst. Similarly, the program or the process can ask for an IO operation, we call it an IO burst. So throughout the life cycle of that process, the process will for some time go into the CPU, and at the end of this CPU burst, it will request for an IO operation, and as soon as it does that, the operating system sends it to the IO queue, IO waiting state, and the process waits in goes into sort of like an IO burst. IO burst is simply the process is waiting for the IO to complete. Similarly, when the IO completes, the process comes back for the CPU, and then this thing keeps repeating itself, and throughout the life cycle of that process, it goes through all these different bursts: CPU burst, IO burst, CPU burst, or IO burst. These are always alternative. And why are we discussing this? We're discussing this because we need to understand the behavior of all the processes which are going through different phases through their life cycle. So every process is going through an IO burst, then a CPU burst, then an IO burst, then a CPU burst. So for example, this is the CPU burst, and this is the second CPU burst of a process. There is a gap between these. This is the IO burst. Similarly, we have another process which has a CPU burst and another its respective CPU burst. So what we can do is, for a single CPU, we can schedule them like this, so that when the first process is waiting for the IO, this part, the second process can go into the CPU. So this is as simple as that. So for example, this was the picture for a CPU, for a process going into CPU, waiting for IO, going into CPU, waiting for IO, going into CPU, waiting for IO. For all of these little chunks of time, the CPU is actually doing nothing. Its time is being wasted. So if we can bring another process into picture, and we can schedule them in such a way that now all the timeline of the CPU is busy, and we have increased the utilization of that CPU. So this is the concept behind why we need to do CPU scheduling. You may already have identified the problem that if we have done even this, there may be small tiny gaps in between. Our objective of this chapter is that we want to minimize those gaps so that CPU utilization can be brought up. CPU utilization be maximum, because CPU is an expensive device, right? So this picture shows us that, this graph shows us that most of the programs, this frequency shows number of programs. It was testing done on various programs, and for CPU burst times of real life programs, and the results came out to be that the number of programs which are really high in frequency have CPU burst duration which is very small. Similarly, the type of processes or the type of CPU bursts which are very large are very less in frequency. Briefly speaking, the number of CPU bursts which are of very small duration are highly frequent, and the number of CPU bursts which are very large are really few. So this gives us a very good margin of doing a very good CPU scheduling, because wherever we see that tiny small gap, we can fit in a new really small CPU burst. Because they're so frequently available, we are always going to have a choice of taking a small size CPU burst and fitting into that small gap that we see on the timeline of a CPU. So this was one aspect to this. This is a part of the operating system. So now we need to understand that CPU scheduler is a type of module inside the operating system which performs CPU scheduling. And what CPU scheduling is, it selects a process out of a number of processes waiting to go into the CPU, and selects a process and sends it to CPU. So that is what CPU scheduler does. And CPU scheduler becomes active on these 4 occasions, and these 4 occasions can be seen or on this picture from chapter 3 of processes. And this picture based on these 4 transitions of states of different processes where CPU scheduler becomes active tells us that whenever the state of a process switches from running to waiting, so whenever a process leaves the CPU, goes into IO. So nothing is going on this side, because we understand that CPU scheduler becomes active to make a decision to select a process from the ready queue, because ready queue has all the processes which are waiting to go into the CPU. But why is this transition affecting this decision making here? The answer to that is that whenever a process leaves the CPU, we need to select a new process to send to CPU, right? Through scheduler dispatch. So that is why we need to make this CPU scheduler active. Similarly, whenever a process goes from running to ready state, so a process goes from running to ready state. So this is the second instance. Whenever a process is interrupted, it is sent back to the ready queue, and because of different priorities, we may need to make a new decision to select a new process to send to CPU, right? So similarly, there are similar other transitions like switches from waiting to ready. So whenever a process comes out of IO waiting and goes into ready queue, that means it is now trying to go into running or CPU. So the operating system becomes active to select a process from ready queue to send to the CPU. So operating system will have to make a choice now. Similarly, whenever a process terminates, so this is simple, because whenever a process leaves the running state and goes out, we need to select a new process from ready state, and that process is called CPU scheduling. So we need to select a new process, right? Similarly, there are 2 different types of scheduling. One is called non-preemptive and the other one is called preemptive. Preemptive is simply that type of scheduling, which are actually these 2 points, 2 and 3. These are types of scheduling when a process leaves the CPU without its own consent. It doesn't want to leave, because you can see from running to ready and from waiting to ready. These are 2 transitions, from running to ready or from waiting to ready. These are 2 transitions which are normally not by the consent or by the choice of a process. A process is not making a choice of coming out of the CPU on its own. Either it is interrupted or it was already waiting for the IO, and IO recently completed and it is now being added to the ready queue. So these transitions are called preemptive scheduling. And similarly, for termination and from switching from running to waiting state, these are 2 transitions which the process makes the choice itself. So process itself says that I want to go into an IO instruction and I want to go into waiting state, and the process itself says that I want to finish myself, or I want to return 0, or I want to exit the program. So these are called non-preemptive. These were 2 types of scheduling. Now dispatcher is a program which simply takes the process which was selected by the CPU scheduler and makes physical arrangements to send it to CPU. It is again part of the operating system program. Scheduling criteria. The CPU scheduling criteria is based on all these different factors which affect the decision making process. The first one is called CPU's utilization, and this is the thing that I mentioned earlier during this video. And why this is the most important thing, because we want to keep the CPU as busy as possible. The CPU is the most expensive part of your computer, and we don't want to waste its time sitting there doing nothing. So if we have multiple programs running, we don't want to keep the programs waiting. This is one way of looking at it, because we want to make the best use of CPU. At the same time, we want to give the user a good experience of using the operating system. So we want to increase the CPU utilization. Similarly, throughput. Throughput is the amount of work done per unit time, a number of operations executed per unit time. So we want to increase that as well. So as much work done per unit time, the better. Similarly, turnaround time is the time the process takes from start to end of its execution, and we want to decrease this time. Similarly, waiting time is all the different chunks of times added together, which are the times during which the process waits for the CPU to become available. So we want to reduce this time as well. And there is another thing, which is the response time. So a process goes into the ready queue, or it is trying to access the CPU, but it is not given the chance to go into the CPU. And the first instant a process makes a request to be executed to the time when it was given the chance to get executed is the response time. So the operating system is interested in reducing this time as well. So this is the different objectives of all the different parameters of scheduling criteria. Like we want to maximize CPU utilization, maximize throughput, minimize turnaround time, minimize waiting time, and minimize response time. Similarly, when all of this is done, and we understand that we have multiple processes and we have only one CPU, for example, and we want to select one lucky process out of all of those processes, and we want to send that lucky process to the CPU. And in doing that, we want to think about this thing for all of the system. The first two things are only related to the CPU. So we want to keep that one CPU in mind. But the three things are related to all the processes in the system, all the processes. For example, ready queue currently has like 20 processes, and the CPU there's only one CPU. So these two criteria are kept in mind, and similarly all these three things are continuously looked after for improvement. So one thing for doing all of this at the same time is utilizing a good CPU scheduling algorithm. So we have a number of algorithms, and we want to make an algorithm which is best and it works best for us.